Okay, fine. Hello, everyone. I am Professor Pankaj Biswas. I am now in live session. If you have any queries, you can ask me. So all of you are very well familiar now about this course, what I feel. That means this course name is Fundamental of Welding Science and Technology. Really, this is a very important and fundamental course related to welding technology. I already discussed about this course in multiple time because at the beginning itself, I introduced this course. Then you have already completed a different week and different, you can say, lecture series already on this course you have completed. So now we have gathered, I think, a lot of fundamental knowledge on welding science and technology. So if you have any queries till now, you can ask me your queries. Just again, I am briefing this course. Actually, this course really a very important course because in this course, generally it will give the fundamental knowledge of various important welding technology, which actually includes most of the important fusion welding technology, especially those fusion welding technology which have traditionally, or you can say conventionally, used in manufacturing industry. It also covered the importance and application of all these welding techniques. This course will highlight the safety precaution to be followed in different welding techniques. This course also covers the physics and principle of welding process, especially fusion welding process. Already you are very well familiar. And at the end of this course, you will also learn about the welding defect and its different inspection process. That and even in a that means different inspection process, as well as how we can detect those defects. That means destructive testing as well as non-destructive testing related things also I covered in this course. So if you have any queries till now, yeah, Mukesh, hi. If you have any queries, you can ask me. Mukesh, thank you already raises. And if you have any queries, you can ask me. Actually, last week, actually, one of the students, he was asking, sir, can you please elaborate the different types of efficiency which we use in this course or which we use in welding techniques? Definitely, we can again explain, though I have covered these topics in what it's called this course itself. Generally, if you want, I can again elaborate these things in online session also. So I'm elaborating this thing right now. So in welding techniques, there are generally two different types of, you can say, heat source efficiency are there. One is called two types of, you can say, efficiency we use. One is called heat source efficiency. Another one is called melting efficiency. So what are those things? Little bit more details actually I'll discuss by writing here. So what I told you, there are generally two different types of, you can say, efficiency terminology we used in welding process. One is called heat source efficiency. Another one is called melting efficiency. First of all, what is heat source efficiency that I am discussing? Then it will be, then I'll discuss about what is called melting, or you can say heat transfer efficiency. So all of you are very well familiar generally in case of a welding process. There we use a power source. So one of the terminal of the power source is connected with electrode, you can say. Another terminal of the power source is connected with workpiece. This you are very well familiar. So in between this workpiece and electrode, you know, there are arc. There is the arc. This is the arc. and this is your electrode, and this is your workpiece. So what is heat source efficiency? Heat source efficiency means this power source or welding power source that you can say, it generally supplies some, you can say, nominal rate of heat it supply. So this nominal rate of heat you can represent in terms of, this heat is supplied by this power source is Q nominal. That is actually equal to the, you can say, current V into I. That means V is voltage, welding voltage, and you can say this is current of the power source. So you can say power source voltage and power source current, V into I. Its unit is in watt. These are very well familiar to you. This is called nominal heat. So whatever the heat this power source is supplying, all the heat is not going to the workpiece. Some losses are generally occur in between this, what it's called workpiece and power source. Like some losses occur in cable, some losses occur in arc, like due to convection, conduction, and all these types of phenomena in some sort of heater generally loss in between this workpiece and power source. So that heat, you can say that that heat generally supply from the arc to, you can say, workpiece. So after loss of heat, some heat, let us consider Q amount of heat. This is actually, you can say, this is the rate of heat transfer from heat source to workpiece. Q is the rate of, you can say, heat transfer from heat source to workpiece, that you can say. So this rate of heat transfer from heat source to workpiece, its unit also is watt, or you can say, or you can write as joule per second. Now, what is heat source efficiency? So heat source efficiency you can represent in terms of eta H is heat source efficiency. This is equal to your, you can say, heat from arc to workpiece, that is, you can say, Q. So here I am converting this Q in terms of joule, energy actually. So that's why I am just multiplying with this in terms of T weld. T weld is the welding time. That means let's T time, the welding is done. So Q into T weld, its unit will be joule. This amount of heat is supplying from heat source to workpiece. This divided by whatever the heat supply from a heat source. Heat source, that is actually your Q nominal into T weld. So this already I discussed. Q now, so Q into T weld. So T weld both this unit also at that means at FCSA, whatever the unit will be, that unit also will be joule, because watt into time is joule. That means with energy, with power, if we multiply time, that convert to energy, that you know. That's why this T weld will be cancelled out. So you can say heat source efficiency is equal to Q divided by Q nominal. Already Q I had discussed, that means Q is the heat transfer from arc to workpiece, whereas Q nominal is the heat supply from the workpiece. That it supply from the power source. That is actually your voltage into current. Now, this Q calculation, that means how we can calculate this Q value. This is already discussed in details in this course itself. Again, I am discussing. This Q generally you can calculate with the help of calorimeter. By using calorimeter, you can calculate this, what it's called. You can say this heat from workpiece, how much heat is applying from arc to workpiece, that you can calculate by using calorimeter. How? Little bit I am just discussing. Generally, what we used to do, if let us consider this is a plate. In this plate, all of you are well familiar about calorimeter, so I am not going in more details about calorimeter. So let us consider this is the arc. So you see, this arc generally supply heat in workpiece. So this is your arc. So this arc is supply heat to the workpiece. This is the workpiece. So below this, generally what we used to do, we generally use what it's called the calorimeter. So what we can say, in other form also you can check it. Let us consider this is your arc. After that, at the below of this arc, you can put the calorimeter. This calorimeter generally contain a inlet and a outlet channel. Through this inlet channel, generally will supply what is called water. Let this inlet have a inlet temperature is T in, and once this by this arc, generally once it supply to this calorimeter, then this calorimeter will heat up this, what it's called, heat up this workpiece, then what it's called calorimeter water. So what happens once this water come out from here, then what happens here, you will get a temperature, let us consider T out. So how much heat is generally, you can say, transferring from arc to workpiece, this you can calculate with the help of this calorimeter by raising the inlet temperature by heating of this arc of this water, you will get a output temperature, correct? Now, how we can calculate this here, you can say heat transfer amount. So you see, due to this, you can say input output temperature, this temperature rise, let us consider, is taken place at a time of T weld. That means up to T welding time, this temperature is rising due to the flow of what is called water through this calorimeter. Let us consider their mass flow rate of water is W. Heat unit is, you can say, kg per, let us consider second, or whatever it is. Okay, so kg per second is the mass flow rate of water which is entering in this inlet and it is coming out from the outlet. So how we can calculate the how much heat is coming to the workpiece by changing the temperature, that calculation part actually I am showing. So here generally Q is the, let us consider the heat which is transferring from arc to workpiece. These things, let us consider Q is, its unit is watt, W, and T weld, once we will put multiply with this Q into T weld, let us consider T weld's unit is second. So this unit, this complete unit will become now joule, because watt into time second is joule, is the heat energy. Now this is equal to, you can find out, this equal to find out this wall heat, this mass heat is responsible for raising the temperature of the calorimeter from T input to T output. So let us consider this thing, just here I am showing. So this thing is, let us consider 0 to, I am that means to raise the temperature from T input to T output, let us consider this temperature is taken place. That means this temperature time is taken place at a time of T weld. What I am telling, understand? Then 0 to, that means this T output, this time range, let us consider 0 to, I am just considering at a very large time scale, alpha. So W. W is the mass flow rate of water. This unit is kg. This is the kg per second. Let us consider the specific heat of the water is C. So what W into C I have already put here. W unit is kg per second. C unit joule per kg Kelvin. Kg into Kelvin or centigrade, whatever it is. Into what it's called? Into T output minus T input into dt over the period of time t. If you just calculate this value, then you will get its unit also, because T output minus T input, this unit is Kelvin, and your dt time, dt unit is the second. If you put these things, what you will get? This second cancel out, kg cancel out, Kelvin cancel out. So this full unit will also become joule, that you can observe from here. So with the help of this concept, by calorimeter raising temperature for a time of dt, for a time of alpha or t well, you can easily find out what is the Q value. So here Q will be your this right side part divided by your T well. If you divide, then you can easily find out what is the Q value. So if you can calculate this Q value, so heat source efficiency is equal to, you can say, Q divided by voltage into current, V into I. So V into I is known to you from heat source, how much, what is called voltage and current you said, that you can easily calculate. You can easily check, you can say, with the help of voltmeter and ammeter are there in welding power source itself. And Q are calculating by using this calorimeter. So you can easily calculate what it's called, what is the heat source efficiency. This is the concept of heat source efficiency calculation. Apart from this thing, generally there are another efficiency term also we use. What are those things? Just I am going to show. That is generally called, you can say, melting efficiency. Melting efficiency. This is also a very interesting, you can say, concept. This melting efficiency is represent, let us consider eta m. So melting efficiency, whatever the heat is coming from arc to workpiece, all heat are not utilizing for what it's called, melting the, you can say, plate and weld zone, that you can say. Because that much heat is not required for melting. Some extra heat also coming, that you can say. Because let us consider you are doing the welding for mild steel. This mild steel have a melting point temperature. So here, like, mild steel have a melting point temperature within a range of around 1540 degrees centigrade or 1500 degrees centigrade, that you can say. So, whereas during welding, you will observe that here the temperature is ranging around 2000 degrees centigrade to, you can say, around 2500 degrees centigrade in case of arc welding. So in this weld zone, here the temperature is coming around this much. So you see, but you are generally required just to melt this workpiece as well as weld metal. Weld metal means electrode metal, to join this region. Correct? But you see, you are getting a temperature range which is much higher than, you can say, 1540 degrees centigrade, that you can say. So you see, all the heat are not required to melt the, you can say, melt the plates. Some extra heat are also coming, that you can say. That's why what happens here, melting efficiency is used. Melting efficiency, you can say, how much heat required to melt the weld metal and, you can say, base metal, divided by how much heat is coming from arc to workpiece. So already that means eta heat source efficiency is equal to Q divided by V into I, voltage into current. So from here you already got the idea what is how much heat is coming Q, that is your Q coming from what is called coming from arc to workpiece, that you can easily get from the what is called heat source efficiency or by calorimeter estimation. So that is actually here is your input. So efficiency always is your output by input, that you know. So in case of melting, you can say efficiency, your input is now known. Input is your Q. That means whatever the output was for heat source efficiency, that is the input for melting efficiency. Now, what is the output here? Here your output should be how much heat require, how much that means you can write how much heat require to melt the base and filler material. Filler material. That is the heat required to melt the base and filler material. That means, and it's raise the temperature up to melting point temperature. That you can say. That's why here just I am just representing not in power. So heat in, once it is in joule, then Q into T weld you can write. So this top part you need to find out. This Q into T weld, this is now known to you. This you can put as eta is V into I. This is now known to you, correct? Into T weld is known to you. Now you need to find out what it's called heat required to melt the base and filler material. That you can find out by using this equation, like A into base into what is called V into T weld. What is this? That I am just discussing. Into A's base plus A into filler into V into T weld into A's filler. What does it mean? So what happens? A into base means after welding, once you take the cross section, you will observe that your bead geometry will become like this. Your bead geometry is become like this. So this bead geometry, some portion is contained what is called filler material. Let us consider this much a cross-sectional area is filler material. And let us consider this much melting material is coming, where the temperature goes beyond melting point temperature, is here the cross-sectional area of base material. That means base material melting area is this much. This is, you can say, a cross-sectional area of filler material. Okay. So this base material and filler material cross-sectional area, if you can find out, then what happens? You can put this thing A base and A filler. Okay. Now with this, if you multiply with velocity, then you can say, well, velocity into time, this will give you the length of weld. So how much length of weld will be there? So A base into L, V into T weld means V is, unit is meter per second, T unit is second. So this meter second cancel out. So your V into T weld give you the length of the weld. Let us consider L. And here your A's base is a very important, you can say, energy. That is the A's base is the heat energy required to, you can say, heat energy required to raise unit volume of base material to melting point temperature and melt it. So A's base is the heat required per unit volume. This you should keep it in mind. So this is the total volume of base material. This is the base material, you can say, heat required per unit volume to a temperature of melting point temperature. Okay, so this will give you the heat required for base material. So this total amount gives you the heat required for base material. This you can say into, you can say here, this I am writing in instead of these things here I am writing J base. That means how much heat required for base material. How much joule of heat required for base material. Plus this A filler into V into T well will be A filler. That means whatever the cross-sectional area you got, this A filler material into V into T well, again length of the weld. This will give you the volume of the filler material into H is filler. Again, H filler is a very important term. H filler is the heat required per unit volume of filler material to raise a temperature up to melting point. This you should keep it in mind. So this will give you the heat required to melt the filler material. So that I am writing J filler divided by whatever the heat you are supplying, that is your heat source efficiency into V into I into, you can say, T weld. Correct? This is a very interesting thing. So these total things you can write. Heat required for base material to raise a temperature up to melting point temperature, because this J base, because H base unit is joule per, you can say, volume. Joule per volume is the unit of H base, and A base into L is its unit is volume. That means meter cube, that you can say. This volume, this meter cube, just here I am writing, let us call meter cube. Here also, this, instead of writing volume, here I am writing meter cube. Okay, so this meter cube will be cancelled out. So J base will come plus J filler will come. Then there will be eta is V into I into T weld. These are the things you should keep it in mind. So J base, J filler plus eta into V into I. So this is generally called melting efficiency. Very simple concept of melting efficiency is generally all the heat is not required to melt the filler and base material. So whatever the heat is supplying to the workpiece, all the heat is not utilizing for melting purpose. Some extra heat also coming. So that's why melting efficiency also required to know. That means for melting purpose, how much heat is required, that is actually your output. Then your input is how much heat is supplying to melt the or to the workpiece. That is known as melting efficiency. So you got the idea. Melting efficiency is equal to J base plus J filler divided by eta is Bi into T weld. This you should keep it in mind. Okay. These are the question actually one student asked me. If you have any queries, you can ask me further question also. Now another actually participant of this course also asked me another question. So I told him that actually I'll discuss this thing in what it's called. I discuss these things in. Okay, whether I share these things? Yes, share. So what you 1 minute. So here you see the things which I have discussed. So you got the idea about what is called heat source efficiency. Eta is equal to, you can say, heat supply from arc to workpiece Q into T weld divided by heat supply from power source, that is, you can say, Q power or Q nominal into T weld. So this Q into T weld, that T weld cancel out, you can write as heat source efficiency equal to Q by QP. This QP is equal to your voltage into current. That you can write. And I already told you how this Q you can calculate from the calorimeter experiment, or by using calorimeter you can find out this Q value. That also I have already discussed. That Q is equal to, you can say, Q into T weld. This equation already I discussed. 0 to at a particular time T, W is the mass flow rate of water into C into T out minus T input of calorimeter into dt. Here C is called a specific heat. Its unit is joule per kg Kelvin. And this W unit is what is called kg per, you can say, mass flow rate, kg per second. Okay. And T is its unit is Kelvin. And this dt unit is second. So by this, if you just calculate the things, you can find out how much, what is the Q value. And this voltage and current you can calculate with the help of voltmeter and ammeter. Now, I also discuss about melting efficiency. So melting efficiency is the how much heat is required for melting the base material and filler material, because all the heat is not required. Whatever the heat is coming from arc to workpiece. So now what is the heat coming from arc to workpiece? That is your Q. So that all the heat is not required. So here how much heat is required to melt the base material and how much heat is required for melt the filler material, that you need to calculate. That will be your output for melting efficiency, and your input will be the heat supply from arc to workpiece. That is actually you can write as eta is V into I. This already I have discussed. Now, another participant of this course asked me another queries. He asked me, sir, can you please explain little bit about the concept of solidification cracking? Solidification cracking. So little bit I am discussing about solidification cracking also. Then solidification cracking also you can called as hot cracking. This you should keep it in mind. But hydrogen embrittlement phenomena, whichever I have discussed, that is generally known as cold cracking types of phenomena. So, there can be two types of cracking. One is solidification. That means during solidification time, whatever the cracking is occur in welding, that is generally called solidification cracking. Whereas you can say cold cracking generally after welding, once it cool down, after 1 day or 2 days, or even after cooling the plate itself, generally there is occur some cracking types of phenomena. That is generally called cold cracking. That means once it come to what it's called room temperature level, there are also some crack can occur. That is occur mainly due to hydrogen embrittlement types of phenomena, which I have already discussed. Now, solidification cracking also is a very important phenomena in case of welding, because if you will not take care properly about this phenomena, then what happens in your weld joint, there can occur some cracking. So, what are the factors generally affecting this solidification cracking that you need to know? Generally, this solidification cracking is dependent on weld metal composition. First. Second, whatever the grain, you can say pattern are there. That means whatever the columnar grain you observe in weld zone, that grain orientation, that means you can say weld solidification, it depends on weld solidification pattern. That means how the grain means oriented during solidification. And another things also, strain on the solidifying weld. That means how much strain are there. It depends on also that also strain what is called one, the solidifying weld. These are the factors which affect the solidification cracking. Generally, if we can control these different aspects, then what happens? We can eliminate this solidification cracking types of phenomena. Generally, by using weld metal composition, there we use a very interesting what is called terminology, that is called UCS. UCS is called units of cracking susceptibility. This is depends on well metal composition, that you can say. So this you can write in the form of, generally in case of submerged arc welding, there was a study for because in case of submerged arc welding, solidification cracking phenomena is very frequently it's observed. That's why there was a study on this. There it is established this UCS. You can write this is actually your 230C plus 190 into sulfur S based on this well metal composition. A 75P plus 45 NB, all are material composition on well metal, minus 12.3 silicon, minus 5.4 manganese, minus 1. So based on this equation, generally, what this UCS, units of cracking susceptibility, this is generally raised. Now this UCS value, based on this, that means based on this value, if one thing you should cover, in case of bar welds, generally if this UCS value is less than 25, then what happens? You can say your weld metal is quite free to solidification types of cracking phenomena. This you should keep it in mind. That's why here one thing you can observe, higher the carbon percentage, sulfur percentage, phosphorus or niobium, these are generally responsible for, you can say, UCS. That means is promote the UCS. That means higher the value of C, that means if C increase, sulfur increase, phosphorus increase in your weld joint, NB increase in your weld joint, then what happens? You can say your UCS also increase. So that's why in weld joint, if your sulfur, phosphorus, niobium, carbon percentage is more, then what happens? There is a chance of what is called higher UCS, and there is a chance of higher solidification cracking. This you should keep it in mind. Now, then which one generally deteriorate this UCS phenomena, or which one generally help to prevent the solidification cracking? Generally, the silicon, manganese, these are the, you can say, material which or metal which help. These are the actually elements, actually material, or you can say these are the element. If the percentage of silicon, manganese is more in your weld composition, then your SS will be reduced. Then your what it's called weld solidification cracking also will reduce. This you should keep it in mind. This is one aspect. Second aspect is weld solidification pattern. So what we observe that once you do the welding, then you can see generally your weld material columnar grain, generally it start from boundary of the what is called boundary of the solid material. These types of grain boundary growthing have a name. This is called epitaxial grain growth phenomena. So these types of columnar grain, sometimes this columnar grain can grow this way. Sometimes this columnar grain can grow in downward direction also. That means in some cases your grain orientation can be like this. This types of phenomena can be there. Downward direction. Okay. So here it create. So here you see, if you see here the angle is less than 90 degree, that you can say. Here in this case, if it is downward direction, then your angle of the grain here is more than 90 degrees. So less than 90 degree here it is. Here this is actually your angle between this, what is called, if the grain orientation, columnar grain orientation is downward direction, then what happens here? Your angle is greater than, you can say, greater than 90 degrees. So if your grain orientation is this, that means where the angle between the two side grain, if it is grain orientation is upward direction, then what happens? You can say your chances of solidification cracking is less. It's help to prevent solidification cracking if your grain orientation is upward direction. This you should keep it in mind. And if it is downward direction, then what happens? Segregation of the, you can say, impurities of the weld material can be accumulated here. So that can create some what is called compressive types of strain. Some strain phenomena here it can raise, which promote the, you can say, solidification cracking phenomenon. These are the things you should keep it in mind. So generally solidification cracking is depends on, you can say, very important factor. One is UCS. So if you can have a UCS value less than 25, it depends on weld metal composition. Then what happens? This and your grain orientation. If you can say control this phenomena, that means UCS less than 25, then what happens? You can prevent the solidification cracking types of phenomena. So this all about what it's called solidification cracking phenomena. How we can prevent it. And also one of the students asked me what are the different types of efficiency used in welding process. That also I have already discussed. And I observe here no further queries are there. If you have any queries again, you can ask me. So no further queries are there. Yeah, one of the students asked me, sir, I am working in laser welding parameter control for AI-based model making with neural network. Can you please give some idea about the laser welding parameter control? This is also a very interesting phenomena. For this, actually, you see, I'll provide you instead of, because this is not the part of this course itself, you can directly contact with me about this course, because in case of laser welding, the process parameters are quite different than fusion welding process, that you can see. Because in case of laser welding process, there are scanning speed, then what happens, laser power, and laser efficiency terminology also different over there. Okay, generally how to, there are some standard distance that you know actually, because as you are working in this field, so there are different types of parameters are there. That is standard distance, spot size, whatever the spot size, that depends on that is standard distance. Then laser power, that means how much power is supplying and how much power is coming to your workpiece. That is also depends on, you can say, that is, you can say, your heat source efficiency. Laser have a heat source efficiency. It depends on the surface quality of workpiece material that you are very well familiar. So that you need to decide, that you need to first calculate. After that, generally you need to control your process parameter. Process parameters are generally, you see, scanning speed is the main process parameter, and standard distance or spot size, you can say, the main process parameter of laser. As well as laser power is also there. That power, if you keep one of the parameter constant and if you vary those things, you will get different types of parameters and different quality of welding. Based on this different parameter variation, you can decide first what you can do. First, you need to let us consider you have decided your spot size. You decided your what is called surface quality. That means surface quality also, if it is very shiny one, generally laser is light, so it have a reflection, that you know. So higher the reflection, higher will be the higher will be the heat loss. So lesser will be the heat source efficiency, that you can say. So that's why what types of surface quality will make. So you can consider another parameter also here. That means by considering different types of, you say, surface color, by putting surface painting. Like what happens, you can put some black types of surface coating, gray types of surface coating. What I'm telling, understand? By this, you can improve the what is heat absorption capacity of your laser beam to the workpiece. That also you can consider another parameter. What I'm telling, understand? So different aspect, different parameter you can consider for laser welding. Though this is not the part of this course, but if you want more detail about these things, you can directly contact with me. Where I have my what it's called contact number, as well as my email ID. You can directly mail me, no problem, Prashanto. So just here you need to consider scanning speed, laser power are the parameter, as well as you can consider surface quality. So laser power is a parameter, that laser power, scanning speed, as well as stand-up distance. These are the very important aspect you need to consider. Okay. And now this surface quality also have another effect. That means that only define your what is the heat source efficiency. What I discussed already here. That heat source efficiency generally in case of laser is responsible for the surface quality of your workpiece, because that's why you know that for joining of aluminum by using laser is very difficult, because it's a shiny surface, na? Because surface quality have a different effect for power. That means laser power means, that means light power absorption capability. So if you want more details about these things, you can directly contact with me, because this will not be right forum to discuss, because this is not the part of this course. I can discuss more detail about these things. Directly contact with me. Okay. Thank you. If you have any further queries, you can directly ask me. Yeah, which are related to this course. I think no further queries are there. So I think we can quit here. Hello? 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 Shall I leave? Hello? Yeah, shall I leave, bhai? Actually, no further queries are there. Okay. So I am leaving. Eh? Okay. Thank you, bhai. This one actually I was telling. Okay, thank you.